Hi, everybody. Welcome to lecture number 14A for Physics 151. I've decided to split lecture 14 into two smaller parts. 14A is all about elastic force and Hooke's law, so that'll be our main topic for this short lecture. And it corresponds to tutorial 14A as well for example problems. 14B will be about friction, static and kinetic friction. So first, let's start with a description of what we mean about elastic force. When a spring is either stretched or compressed away from its equilibrium position, then it's going to exert a pull or a push to try to get back to its original position. So our nickname for this sort of behavior is that the spring exerts a restoring force. So if we stretch a spring, well, first of all, I should say the equilibrium position is essentially where the spring is sort of relaxed. If you let go of the spring, if it doesn't move anywhere or doesn't go anywhere, then it's at its equilibrium position. If we then stretch it to a longer length than that, then the spring will pull back with the some amount of restoring force. Or if we compress the spring, assuming the coils are not already touching, if we compress the spring from its equilibrium position, it will push back to its original position with a restoring force. The strength of this restoring force that an ideal spring exerts is given by Hooke's law here, which I've written in sort of two different forms, but they say the same thing. Hooke's law is special because it shows us that the amount of force is directly proportional to the amount of displacement. In other words, if delta L is the amount of displacement, distance-wise, if this is the distance that we either stretch or compress a spring away from its equilibrium position, then you can see that the amount of force that the spring is going to exert is in direct proportion, right? Or in other words, it behaves linearly with respect to that amount of displacement. K is a constant that varies from spring to spring, and it's basically a measure of how stiff or strong that spring is. We call that the spring constant for that spring. And it's measured in force per distance. In other words, it's measured in the amount of force, restoring force that a spring exhibits when you displace it by a certain number of meters of stretch or compression. What that means is that K, if the K value is very small, that means the spring pushes with very few newtons for every meter that you stretch or compress it. And if K is large, that means the spring pushes back with many newtons for every meter that you stretch or compress it. Okay, so small values of K are for springs that are soft and loose and easy to stretch or compress. Large values of K are for very stiff springs, very hard springs that compress very little or stretch very little, even when you impose a great force on them. Now, if we decide to define the x direction, the positive x-axis, along the length or axis of the spring, then we can rewrite Hooke's law in this fashion down here. And x is the amount of displacement that we stretch or compress the spring by. K is the same constant. And the amount of force that the spring exerts then is in the opposite direction to the displacement. So if you stretch the spring pulls back, but if you compress the spring pushes back in the opposite direction that you've displaced it. X is defined as 0 at its equilibrium position. So that means when you let go of the spring, it's not going to exhibit any push or pull at all, and it'll stay where you release it. Now, a few quick notes about this, since we're talking about the equilibrium position. When you have a horizontal spring, it's basically when the spring is relaxed and the coils aren't exerting any force. For a vertical spring, it could be that some amount of mass is suspended from the vertical spring, and when you let go gently, the mass stays put. Then technically the spring is stretched at that point. However, it turns out that mathematically we can offset the equilibrium position by that amount, and we can reset the equilibrium position at that new location. This is extremely useful. This means that even if there's some amount of mass already suspended from a spring or already resting on top of a vertical spring, we can we can decide to redefine the equilibrium position x equals 0 at any location where, even though the spring is stretched or compressed, when we let go, it will remain at rest. So we can redefine that to be a new equilibrium position if we want. So we can say x equals 0 at that location. Okay, so that's very useful. This will make a little more sense when I do an example problem in just a minute. And then finally, in real life, springs are not always ideal. First of all, they have some amount of weight and inertia of their own. This causes a little departure from Hooke's law, but it's more important later when we talk about oscillations of springs. Um, real life elastic objects do not always obey Hooke's law, meaning if you stretch them twice as far, they don't always exert twice as much force. So this is especially true for elastic bands and bungee cords. They just simply don't follow Hooke's law for large displacements. And finally, real life springs have a limit about how far you can stretch them. Hooke's law doesn't have any limit on how big X can be. An ideal spring will always obey Hooke's law for any amount of stretch or compression. However, real life springs eventually will deform plastically, meaning they'll permanently bend out of shape, or they may even break. Okay, so let's bring all this to life with an example problem. I'm going to use problem number 1 from our tutorial sheet. So I'm going to switch to a desktop camera and do this example on pen and paper. Okay, great. So as you can see here, problem number 1 actually has 2 parts. It has the same spring displaced by the same amount, only in part 1A, that spring is going to be positioned horizontally and displaced to the right. However, in part 1B, that same spring is going to be positioned vertically. I don't have a picture here, so I'll make a little sketch. And it's going to have the same spring constant, so same spring, only we're going to displace it vertically. Okay. So first of all, let's take a closer look at 1A. Suppose that we have a spring that has a constant of 10 newtons per meter. How much force would we need to exert externally in order to be able to hold it at that position, displaced 25 centimeters from its equilibrium position? All right, I'm going to just go ahead to save time. Normally, to draw a free body diagram, we would reproduce the mass over here all by itself and then draw the force vectors on it fresh. But to save time, I'm just going to use this block right here as a free body diagram for our purposes. And I'm going to say, all right, what are all the forces that are currently acting on this mass? We know that it has a weight, which acts downward toward the center of the Earth. Or if you want, we can call that W, lowercase w. We know that there's a normal force from the surface of contact here, the table, or you can call that just lowercase n. Okay? Now, in this particular case, those two forces are not going to be very interesting because they exactly cancel each other out. Then there's this external force from the person to the right. And then we know that because this spring is already displaced to the right, Hooke's law tells us that it must be pulling back on this object here to the left. So there must already be a restoring force. We displaced the spring to the right, so there's some sort of restoring force pulling to the left. So I'm going to call that the spring force. You could call it the elastic force if you wish. Okay. All right, great. I think that's a complete inventory now of all the forces acting on this spring. Now let's apply Newton's second law to this. Okay. So I'm not really interested in the vertical direction. In fact, we can apply Newton's second law. We can just eyeball it, and we can see that in the vertical direction, the normal force is just equal to the weight, and there's no acceleration at all in the vertical direction. So it's just equal to mg mg. But we're interested in the horizontal direction here to answer the question about how big F sub p should be, the applied force. So Newton's second law. So let's look at the x components. Now, if we're holding this mass at rest at this location, then what that means is this right-hand side here is just going to be 0, right? In other words, it's a static situation. And on the left-hand side, we have the x components of all of the forces. So the normal force and the weight have no x component at all. We can just see by inspection. And we can see that the x component of Fp is the entire magnitude in the positive x direction. And we can see that the x component of the spring force is the entire magnitude in the negative x direction. All right. So what this tells us is that the magnitude of Fp should just be equal to the magnitude of the spring's restoring force. These are both magnitudes. We know that the magnitude of the spring's restoring force is going to be equal to k times the distance that it's displaced. Okay, so notice I'm dropping the minus sign here because all we care about is the absolute value or magnitude of the restoring force. 10 newtons per meter, 0.25 meters, and that's equal to 2.5 newtons. So the spring, when we displace this spring 25 centimeters to the right, it's trying to pull back, right? It's trying to restore itself to its original equilibrium position with a force of 2.5 newtons to the left. So if I want to hold it at this position, displaced, then I need to exert an equal 2.5 newtons to the right. So that way now the two forces will sum to 0 in the horizontal direction, and the system will be in static equilibrium. So that's answer choice D. Now, if we take a look at the second problem, 1b, what we see is the same spring is positioned vertically. And we want to hold it again at 25 centimeters of displacement. But this time, instead of holding it with some sort of external force, like a person just tugging on it, we want to use a mass to do that instead. So the weight of this mass is going to be the thing that's responsible for holding the spring in position. So what I'm going to do is I'm going to just sketch what this sort of looks like. So here's our spring. And the spring at this point has already been displaced 25 centimeters downward by this mass right here. So we know that if I want to use this like a little free body diagram, we know that there's a weight pulling downward. And we know that there's this restoring force of the spring pulling upward. If we now apply Newton's second law in the vertical direction, we'll add up all the y components of all these forces. Although, well, you know what? I think that's fine. Yeah, we'll just call this the y direction, which is along the axis of the spring. Traditionally, when a spring's involved, it's often the case that we'll call it the x-axis, even when it's vertical. But in this case, that's fine. We're just going to take the magnitude of the Hooke's law anyway. And we know in this case, again, it sits at rest, right? This is going to be static equilibrium. So when you let go of the mass, nothing moves. The y components of these two forces are going to be the spring's force pulling upward and the weight pulling downward. So that means that spring force and weight have equal magnitudes. So notice how this is the same, very similar to the previous situation. The only difference is now the external applied force is the weight of the object that's being hung at the bottom of the spring. So this is going to be equal to k times d, right? Again, we just care about the magnitude or absolute value. And then on the right-hand side, this is m times g. So what we find, now This will generally be true for any mass that's hanging from any spring in static equilibrium at rest. What we actually want to know in this particular case is what's the value of the mass given the displacement and the spring constant. So we can solve for it in this particular case. The mass is going to be equal to K times D divided by little g. Now we're given these values, so we can go ahead and plug them in. 10 newtons per meter, 25 centimeters converted to meters, and then 9.8. This is a constant, right? And this turns out to be about 0.255 kilograms. Now this looks like a two significant figure problem, so if I round this off to 0.26 kilograms, that looks close. That looks like this answer choice here, 260 grams, right, for two sig figs. All right, so we've seen a spring example here where here is a spring, in 1A, we have a spring in a horizontal position where the weight of any object that's attached to it is irrelevant and is simply counteracted by the frictionless surface down here that's under the mass. Whereas when we hang a spring vertically, there is no normal force because this mass is free. It's not touching any surface, right? It's not in contact with the surface. And in this case, it's the weight of the mass that it has displaced the spring by some amount d from its original equilibrium position. So at this new equilibrium, we can find out how much mass it takes to displace this spring by an amount d from its unladen equilibrium point. All right, great. I'm going to just go back to our final slide now. So our final slide is a quick review quiz. I recommend that you pause this video and try and answer these 4 questions based on what we've covered and what you might have read in the chapter about springs. And then resume the video as soon as you're done, and we'll quickly go over the answers. Okay, welcome back. Here are the answers for these 4 questions. And just to quickly review this, if a spring is displaced to the right, then of course it's going to pull back to the left, and that's why it gets the name of restoring force. When a spring is displaced by a certain amount of distance, if it has a restoring force of F, let's call it the distance d, the restoring force F naught or F0, then if we quadruple d, what will the restoring force be? It'll be 4 times as large. And we know this from Hooke's law, right? Hooke's law says that the strength of the restoring force is directly proportional to the amount of the displacement. So if you quadruple the displacement, you quadruple the restoring force. What's the spring's constant? If we are given a displacement of 1 centimeter and a force of 25 newtons, well, in that case, you can see from Hooke's law right here that the spring's constant is going to be equal to the restoring force of the spring divided by the amount of displacement. So that's going to be 25 newtons divided by 0.01 of a meter. If we want the answer in newtons per meter, then that turns out to be 2,500. So this is a fairly stiff spring. If you stretch it by only 1 centimeter, it pushes or pulls back on you with 25 newtons, which is about 5 pounds of force. And then finally, can a spring ever exert a force perpendicular to its axis? No. Springs can only ever act along their axis. So springs can exert forces that either pull or push along the axis of the spring, but they can never ever exert a force that would be at right angles to the spring axis like this. Okay, so springs simply don't behave in that way. It's kind of like a little bit like tension in ropes. It can only act along the cord, but not at right angles to it. Okay, so at this point, I recommend that you try the remaining problems on tutorial 14A. There's two more questions to practice this, and proceed to online homework and mastering physics, and work on the first part of homework number 14, which has questions about springs and Hooke's law. Like I said, 14B, tutorial and lecture 14B, and the second part of the Mastering Physics online homework will be about friction, static and kinetic friction.